Um, you can start recording, Kate. Can you hear me?
Yeah, Catherine's recorded.
Okay. Yeah, I'm just checking because last time I was talking to myself. So hello everyone and welcome to today's webinar. My name is Gosia Szypulska and I'm the current chair for the Southeast branch. Today's presentation is from the series of corrosion protection, high-speed railway systems and buried pipelines. The presenter is Ken Lax. He's corrosion specialist from Corro Consult UK Limited. So before we start, I would like to ask everyone to mute their microphones and turn off the cameras, as this helps with the quality of the call. There is a chat facility where you can type your questions or put your comments, and then all the comments are very welcome. And this session is being recorded and it will be available later on the Pipeline Industries Guild YouTube channel. So Ken, over to you.
Thank you, Gosia. Good afternoon. Good morning, everybody. Thank you for joining us. We hope that you'll enjoy these presentations, which are made on behalf of the Guild Southwest branch, Southeast branch, beg your pardon. Just let me get right. Hopefully everybody's seeing the screen okay. Just to tell you a little bit about the people who've prepared this. It's myself and Richard Lindley and Professor Charalambos from the University of Cyprus, who's a specialist in these areas. This is the fourth in the series motivated by the Southeast branch of PIG. And the aim of them is to explain sometimes complex systems that affect the pipelines in simple language. That means we don't put any mathematics in it or any physics or any science, but we try to explain exactly what's going on so that people who don't have the necessary technical background in electrical systems or in corrosion systems will be able to fully understand what the impacts are of these things. We'll be responding to your questions at any time. If you enter them via the chat option, the kind ladies at PIG will be picking those up and Gosia will be dealing with them at the end. If anything happens with the quality of the system, please send us a chat announcement and we'll try and put it right. So you will be able to see this on YouTube later, and it will be available for download if you so desire. So as I said, the aim is to present technical information primarily intended for members of the Guild, of course, but they do provide it to the general public. But it's for people who have the responsibility for pipelines, but don't have the detailed technical background in this particular topic. And what we're going to be discussing today is the impact of high-speed trains on buried pipelines. Now, those of you who followed the earlier versions of these presentations will have picked up that there's a time element involved with electrical interference on pipelines. Just because the pipeline potential changes very quickly doesn't mean to say that you've got a corrosion problem. And you might be forgiven for wondering why, if this train is traveling at 200 kilometers per hour, how it causes a problem to a coating defect on a pipeline. And these are things we're going to explain to you, along with the safety risk that comes to it, the risk of electric shock. So first thing we need to do is to refresh a little about AC, what it is, and what induction is and what conduction is, because these are the two key elements that affect the pipeline risk. Now, alternating current behaves differently to DC. Because direct current is pretty easy to understand. There are some very simple relationships between potential current and resistance. And basically, the potential is what pushes the electric current around a circuit. The resistance is the opposition to that current. And the current is what you finally end up with, what comes through the resistance. But with AC, it's a bit more complicated, because an electrical current has a magnetic field associated with it, which people sometimes forget about. And the field is actually at 90 degrees to the voltage field. So the voltage or the current fields are in the same phase. And you can see on this little sketch that the little red bits here show how the magnetic field whizzes out to the side here, while the current field drops down to the bottom, and it's in what we call a sinusoidal waveform. But it also has, unlike DC, as well as going up and down, it also moves along a certain track, and that makes it difficult to do the calculations, because you have to take into account the spatial aspect as well. So as you can see, that it's impossible to separate the magnetic field from the electric field. So whenever there's an electric current flowing, there is a magnetic field, and it fluctuates. In the UK, it's 50 times a second, 50 cycles it used to be called, but now it's called 50 hertz. So 50 times a second, you will get this waveform 50 times every second, and associated is that. Now, there's a special effect that takes place when a changing magnetic field hits a conductor, like a piece of copper or something like that. This is how electric generators work. In fact, you have a rotating copper conductor and you have a static magnetic field, or you can have a static conductor and a changing field. The net effect is the same. A voltage is induced as if by magic into the copper conductor. And in this, what we're considering in this case is a steel pipe running alongside the train track, subject to this changing magnetic field. And the magnetic field will induce a voltage in the pipe, and it's related to how strong the field is and how big and how long the pipe is. Normal overhead power lines that you see around you in the countryside, they can be anything from about 5,000 volts up to 600,000 volts. But AC railways are generally 25,000 volts. So the little cables you see running overhead your electric train, they're usually carrying about 25,000 volts. Now, the problem with this voltage being induced into the pipe is twofold. But as well as the induced voltage, we also have to consider the conduction, which is what we mentioned earlier. The conduction is different from induction. In my view, induction occurs by magic when the magnetic field changes, and conduction occurs under different circumstances, under what we call fault conditions. But the majority of the issues that we're going to be talking about today, concerned about, are related to pipelines and induction. And there are some key things you need to keep in mind all the way through this presentation. And that is that the greater the current, the stronger the magnetic field. And that's a universal truth. And of course, the bigger the field, the more voltage is induced. And the longer the conductor is, the more the voltage will be. So when you've got a long conductor like a pipeline and a big magnetic field, you're going to get big voltages induced. But also, If there is a fault on the AC system that's powering the train, what they commonly call a ground fault, that for a short period of time, some of that AC current will also travel through the ground. Literally, it will travel through the ground. So therefore, the pipeline can be affected by that, but for a very short period. And we'll talk a little bit about the periods of fault systems. But generally, short-term conductance effects are not a corrosion risk. That's not universally true, but it's generally true. And we're going to consider firstly the risks of induced voltages and accelerated corrosion. Now, one of the risks you can have on a pipeline can also occur during construction of a new pipeline close to an existing railway system, because sometimes there is enough current flying around on the AC train system to induce a voltage on even relatively short lengths of pipeline. And therefore, anybody touching that and touching the earth, they will get an electric shock. And for construction personnel, this can be quite harmful, not necessarily that they could get a lethal amount of current flowing through them to kill them, but because the sudden shock causes people to have accidents, like stepping into a ditch or falling off the scaffolding, or stepping back onto a road, or stepping back onto somebody else, or stabbing them with a screwdriver. So it's not always the magnitude of the electric shock that causes the issue, it's the secondary damage. And the second risk is accelerated corrosion. Now, during the normal operation of the train, it's quite possible for what they call touch potentials to be above the recommended levels. I've been careful not to put a value in for the recommended level because it varies for different countries and different regions even, but it's normally between 50 and 60 volts, something like that. We have a different value to minimize AC corrosion, which we'll talk about a bit later. So it's possible that during the normal operation of the train, you can get more than 50 or 60 volts induced into the pipeline. And if you happen to be wearing flip-flops and shorts and no gloves, that will very quickly go through you and give you an electric shock. There are different levels of tolerance for people who are wearing insulated safety footwear and wearing gloves and are healthy, but it's always as well to remember that the risk is always there. Fault conditions, however, where you get the conduction effect, they don't normally last for very long because the electrical systems either have a safety shutdown, or in some cases, they automatically change circuits to take away the risk. Something important to remember in respect of corrosion is that we don't always just think about voltages. We think about the density of current, how much current there is in a certain surface area. And for that, we have a different set of criteria. And the other thing to remember is that all of the measurements that we take for pipeline corrosion risk from AC are based on average measurements over a period of time. And we'll talk about that a little bit later in more detail. For some odd reason, humans are particularly vulnerable to currents at 50 and 60 hertz, 50 and 60 cycles. It's all to do with the impedance of the body and so on and so forth. It varies for people. But generally, 1,000th of an ampere can be lethal. If you get 1,000th of an ampere flowing through your heart, it will probably stop. So that's why earth faults are generally cleared in less than half a second. And according to some research that's generally accepted, is that if you can clear the faults within 0.06 and 0.3 of a second, then that area, it reduces the risk of fatal exposure to the voltage. So if we look at stray current, which is probably the larger of the two risks on most installations these days, we do have some standards available to help you deal with this. And these are the standard references that you need to be looking at. Now, the measurements are an important part of assessing the corrosion risk on pipelines, because the data has to be dealt with in a different way. And we use something called a coupon, which is just a piece of steel with known characteristics, with a known surface area, and sometimes with a known thickness. And what we know from all of the scientific work and practical work that's been done is that a surface area of 1 centimeter square is the standard that we use for assessing the risks. It can't be scaled up. You can't say that 30 amps per meter square is okay on 1 centimeter square, and you could have 60 amps per meter square on a 2 centimeter coupon. It doesn't work like that for various reasons. So within the standards, we've standardized on a 1 centimeter square coupon to do all the evaluation of the risks. And there are basically 4 sort of criterion available. The first thing we aim to do is to get the value down to 15 volts or less. And you might see here that I've been careful to say RMS. That's for electrical people, that's very significant. It means that it's an average value. It's the root mean square value of the voltage, because that's important to us in this context. So the first thing you do is apply some mitigation to get it down to less than 15 volts, even though for touch potentials, you can live with up to 50 volts or 60 volts, depending where you are. However, under certain conditions, you can have AC corrosion with only 5 volts. So we can't apply that 15 volts as a universal panacea, but it's the target value that we always aim for to begin with. The next thing we have to do is to measure the current density on a 1 centimeter square coupon. And to do this, we connect a coupon to the pipe, normally via an above ground test post, so that the coupon is experiencing the same electrical characteristics as the pipe. And we can measure the coupon and the coupon current and the coupon potential very easily. And we give a guide of saying it should be less than 30 amps per square meter. But there is a relationship between the cathodic protection current density that we put onto the pipe. So that's only valid under certain circumstances. And then you need to keep the cathodic protection current density to less than 1 amp per square meter if the AC current density is greater than 30 amps per square meter. And then finally, you can look at the AC and DC current density ratios on the 1 centimeter coupon, and they should be significantly less than 5. So this makes it difficult for anyone other than a specialist to determine on what criterion is correct. But I'll explain later on that there is a way around this. There is a device called an electrical resistance probe, which has a 1 centimeter square exposed surface area. And this probe works in a very special way, because we know how to measure and how to calculate the resistance of a 1 centimeter square piece of steel. And we know that there's a relationship between the resistance and the surface area. Actually, the smaller the steel, the higher the resistance. So that means that if you had a coupon of 1 centimeter square and it corroded, its surface area would decrease, so its resistance would increase. And by doing some fancy measurements, we can calculate what the corrosion rate is. And with the electrical resistance probe, you can also measure the actual corrosion rate, the AC and DC current densities, and the ratios between the AC and current densities. So corrosion probes are one way to deal with it. So you might wonder what's the big issue with high-speed trains, because they're a great boon, and there are more and more of them around the world every day. There's a map you can access on the internet which keeps an update of high-speed train routes, and there are more and more all over the world. But the simple fact is, in order to go fast, they need a lot of current. And as we saw before, more current means a bigger magnetic field, which means you get more interference. And a train, let's have taken an imaginary length of 30 meters, traveling at a speed of 200 kilometers, will go past a 1 centimeter square defect in about 6,000ths of a second. So you think, well, that's okay, lots of current, but it's only there for 0.6 of a second when the train goes by, and the train isn't going by all the time. So why is there a problem? What are we worried about? But think again, because actually when we look at the circuit of an electric train, it works like this. You have a section of track between two substations. The train takes its power from, let's go substation 1 and substation 2. It takes its power from these two substations. It picks it up on the overhead wire, takes it down through the train, through the motor, onto the wheels and onto the track, and then back to the substation that it got the current from. So if we imagine a worst case scenario of a long parallel pipe, very well coated, with one small coating defect of 1 centimeter square. And that's a very realistic situation these days, because the high quality of coatings that you can get now and the high level of supervision and care taken during the installation of the pipe means that you get very few defects on well-coated pipes that are installed properly. There are always exceptions to this, of course, and that's what pays my wages. But on this 1 centimeter square coating defect here, you can see that it's subject to the interference of the electric current that's flowing through the track and the overhead power line, because each of them has a magnetic field. It's subject to that while the train is there. And when the train's near this substation and going in that direction, it takes about 90% of its current from here and 10% from there. Then as it moves along to the middle of the track, it's taking 50% from this one and 50% from that one. And then, as you'd expect, when it gets up to this one, it takes 90% from there, and so it moves on. But the thing to note is that this coating defect is receiving the current all the time, the effects of the current. Although that current will be changing in some way, it's under the influence of that interference all the time. So it's not right to say it only suffers from interference for that 6 milliseconds when the train goes by. It doesn't. It suffers from it all the time until the train moves into the next segment and it picks up its power from this and the next substation along the line. And this is an important concept. It's why we insist on taking average measurements of the potentials and the current so that we can determine what the long-term effects are. And there are all kinds of varying factors that come into this, which are a little bit too deep to go into now. We're happy to do it at a later presentation, but there are all kinds of other effects to take into account, which are not mentioned in this simplistic picture. The aim of this picture is to give you the idea that it's a dynamic situation, because the train is always moving and the effect of the current here is always changing, but it's always influenced until it gets into the next section. So in that respect, it depends very much on the timetable of the trains and the length of the train and how many parts of the train are pulling power. There's regenerative braking, which influences it. And there are other things such as harmonics from the system that influence it. These things we're not taking into account now, but they just make the situation worse. Another thing to bear in mind is that, of course, normally you have an up line and a down line on a railway system. And the interference on this coating defect will also be affected by the train on the other line. And that interacts with the magnetic field with the trains on this line and the harmonics generated by both trains. So you can imagine that you get quite a complicated pattern, which is different from when the trains are approaching each other or departing from each other, or they're both at the same time in the same place. It really is quite a complicated state of affairs. And it's something you perhaps need to bear in mind for a little bit later on, is when I mentioned earlier on about how we do these measurements and why we need them done in this way, is that it's a dynamic system, it's a moving system. And when it comes to modeling, you normally just get a static situation, like a snapshot, which is why a bit later on I'll be talking about the cautionary approach you should take from models. So what's important to take away from those little sketches there is that the poor old coating defect is suffering all the time. And if it gets if the current density on the defect approaches a certain level, then we need to do certain things. And if there's cathodic protection on it as well, we need to do certain things. So the question is what we're going to do about the AC corrosion risks. Well, the first thing to bear in mind that corrosion only takes place on the pipe where the bare steel is exposed to the electrolyte, whether that electrolyte happens to be concrete, water, soil. And I haven't discussed in this presentation the corrosion risks that exist on steel reinforcement in concrete, in tunnels and crossings and so on, because this is just related to pipelines, but the same risks are there. So it's not too hard to understand that if you want to get rid of the corrosion, the AC corrosion risk, you need to get rid of the AC, because without the AC, you haven't got a problem. And the reason that the AC is induced in your pipe and it leaves the pipe is because it wants to get back to where it came from. So if you can remove the AC, then you won't have an AC corrosion risk. And the way to do that is to make a direct connection between the pipe and the earth. If you earth the pipe, the current will flow through the earth and it won't corrode your pipe. It will flow through the cable into the electrode you've got in the earth, and it will return to where it wants to go. That's great, but it means that your cathodic protection won't work, because your cathodic protection is there to provide DC current onto the defect to stop it corroding, which we covered in one of the earlier presentations, and the PIG has other presentations on cathodic protection, which are referenced at the end of this. So now you've got the dilemma where you've got the AC on the pipe, which you don't want, but the best way to get it off is to impact on the cathodic protection, which will then allow the pipe to corrode because there's no cathodic protection. So what we have to do is connect the earth of the pipe through a widget that stops the cathodic protection leaving the pipe, but lets the alternating current leave the pipe. And those devices are normally called polarization cells or polarization devices. So you can do that, but of course you have to know where to put those devices and where to put the earthing. And that normally we do by modeling, which we'll talk about a bit later. And we also, to fulfill one of the requirements of the AC protection criteria, we need to keep this current density as low as possible. which is not always the case. Many pipes have too much cathodic protection current. The mitigation of AC safety risks works on the same basis. You need to get the AC off the pipe, however it got there, whether by conductive or by inductive means. And what you have to do is make sure that nobody can touch anything that's connected to the pipe above the ground, like a valve or a test post, or sometimes there are monitoring devices. Anything that anybody can touch on the surface, which is connected to the pipe, can receive an electric shock if there's a voltage on the pipe. So the difficulty there is that you can apply the same techniques to make the pipe earthy, but of course, again, you've got to use these polarization devices not to affect the cathodic protection. But there's also a risk of something called step potentials, which is where the voltage gradient in the soil is so steep that it can cause a significant voltage difference between your legs. And this is as horrid as it sounds. Voltage gradients are easy to picture. If you imagine they're exactly the same as a gradient in the soil. If you have a steep gradient on the ground, a very, very steep hill, then the difference between one leg and the other leg is quite steep. And therefore, it's more difficult to walk because of this difference. Well, it's the same with voltage gradients in the soil. If you've got a very big gradient and you've got one leg at one potential and another leg at another potential, the difference can be enough for current to flow through your body. It's obviously a somewhat bigger risk for longer animals such as horses and cattle. In such cases, what you have to do is make the gradient flat. In other words, you take away the hill. And we do that by putting a grounding mat at the location where that happens. And sometimes you'll see these installed at valves where they can't effectively isolate it any other way. They equalize the potential around the structure so that both legs are at the same potential, at the same level. Now let's get to the joys and the horrors of modeling and the interference of experts. Mathematical modeling has improved a lot over the years, and there are now many companies that offer a modeling service for you. Like any other external service you buy in, some people are better at it than others. And I think it's up to you to be cautious about how you select your modelers, because you make so many big decisions on them, especially if a pipeline hasn't been constructed yet and you haven't got the possibility to take real measurements. And a good way to evaluate the modelers would be to select more than one group of people or company to do it, and then send them a set of fictitious data and ask them all to just do the modeling on that fictitious data. So obviously you don't make it a huge system, just a small system, and then see who comes back with what looks like sensible answers. But they're nearly always static models. That is, they take a snapshot. They say, I'm going to assume 1,000 amps from this substation. I'm going to assume 500 amps coming from this substation. I'm going to assume that the insulation between the rail and the earth is this. I'm going to assume the conductance of the rail is that. I'm going to assume that the earth resistance at the substations is this. I'm going to assume, and so on. They go on all those sort of things. And then they make their calculations. So obviously they're only as good as the assumptions, and it's up to you to provide them with the data they need in which to make those assumptions. And what they normally do is they collaborate with the designer of the traction power system, and they're nearly always done on mathematical models as well. And they model certain conditions. Let's say this one fails and there's a ground short here, or there's a rail to earth short there, and it's awfully difficult to do. So therefore, they do a lot of single static predictions. You can do dynamic modeling, but it's hugely expensive, and it does take a lot of computing power. And really, it's not often necessary. Now, the horrors of models are, firstly, people always believe models. They always believe anything that's presented with a nice graph or a nice plot or with nice colors. And the people who do these things are expert at doing that. And you can, sometimes in the hands of people who don't really understand what's going on, you can be fooled into undertaking mitigation systems that are just not necessary. And that's costly and wasteful and environmentally unfriendly to do that sort of thing. So I think that it would be a good idea to follow the motto of the Royal Society in London, which their motto says, never believe anything anybody tells you. And just be very skeptical about people who come along and say, well, yes, you can protect this pipe. You need 7 kilometers of zinc ribbon in a ditch, and you need this many polarization devices, and you need the coating repaired here, there, and everywhere, and you need to change all your test posts, and you need to electrically isolate all your valves. That's not always true, and you should challenge all of those kind of things, because, for example, if the model predicts that you could have an instantaneous voltage of 100 volts on a section of the pipe, and therefore they say to you, therefore you've got to put a lot of mitigation in to get that down to less than 15 volts. But in fact, if there's nothing for them to touch in that section where there's 70 volts or 100 volts, there's no need to do anything. It's only if there's something they can touch that they'll get an electric shock. And even if there is a test post there, you can easily put in what they call a dead front test post, which is cheap to install, which prevents anybody touching any of the connectors. So therefore, that fulfills the requirements for touch protection. So you don't need to do an expensive voltage drain exercise on the pipe. And similarly, at valves, it may be cheaper and more productive to install a mat around the valve, so that if anybody stands on that mat, their feet are not skewed on a slope, but they're at the same potential. And if they're at the same potential, there won't be any current flowing. And I think that's the big lesson to take away, really, that models are fantastic. You need to check very carefully the people who are doing the model, and you need to be skeptical of all the requirements and challenge all the engineers and salesmen and specialists and experts who come and tell you need to do massive remedial works. All right. So the standards that you need to be looking at really are ISO 15589-1, which is a cathodic protection standard, which is presently just starting a review process. And then the BSEN 50122-2, which is in review stage at the moment, and 50162, which has just been revalidated for 2 years. They tell you, in very round terms, the 50122 tells you what to do to reduce the amount of stray current you produce, and 50162 tells you what to do when you're the recipient of it. But it is focused on DC, not AC, but there are still some useful tips there that can be applied to AC. And for stray current conditions, it's in ISO 21857, which is specific for pipelines. It's a new standard. It was published in 2021, and it's mainly for DC, but there is an annex that shows you how to do the calculation for induced AC. for a simple case, which would allow you to run your own sense check against any model that's produced for you. And in summary, I think you have to expect that if your pipeline is near to a high-speed railway, you can expect some electrical interference. The worst case scenario is if you have a long parallel section of pipe and railway. If you have a pipe that's crossing under the railway, then the risks are much less. If it crosses at 90 degrees, because you remember the graph of the electromagnetic wave, if you change the angle between the magnetic field and the pipe, there will be less induced because the fields will cancel out. So if you can cross the pipeline at 90 degrees, your risk of induced voltage is much less. If you cross it at 45 degrees, it's 50% more. Safety issues have to be addressed. I don't know how the J got in there, sorry. Safety issues must be addressed in terms of touch potential and step and touch potentials. Two typing errors there, apologies. They have to be considered during construction as well as during operation. And if you have a new pipeline going into an existing, being installed near an existing railway, you need to make sure that the safety issues are taken into account during construction. And if a new high-speed railway is going in adjacent to your existing pipeline, you need to think about doing some measurements and modeling to determine where you need to apply any mitigation. But you also need to change your operating conditions so that people who work on the pipeline are aware that there could now be a risk of unacceptable touch potentials on things connected to the pipe. And under certain conditions, there will be risks of accelerated corrosion. So it's something that you need to address one way or another. Now, there are other sources of information. Chris Atkins of PIG, he produced a presentation which is on YouTube about cathodic protection for pipelines. And there are the ones that we mentioned at the beginning that this branch has done. And there are 4 international organizations that deal with corrosion and certification of specialists. And each one of them has got useful information. So thanks very much for attending the presentation. I've tried to keep it on time again. Not too bad, I hope, Kate. And if any of you got any questions, you can always email myself or Richard Lindley at our office addresses, and we'd be very happy to assist you. You can always, of course, contact the Guild. They have a lot of knowledge and expertise within the Guild, and they can always direct you to the right person if you want to talk about planning, rights of way, crossings, legal aspects, coatings, that sort of stuff. The Guild is there to provide that service to you. So thank you very much. And if there are any questions, we'd be delighted to answer them now.
Thank you very much, Ken. That was very interesting presentation. As Ken mentioned, there are a couple of them already, which are uploaded on the YouTube channel. So please have a look there. Also, I'm hoping to negotiate with Ken a few more presentations on cathodic protection. So we will try to have more of them. We've got a couple of questions. Ken, first question, would you advise that all underground pipelines underneath railway tracks should be sleeved to minimize the effect of induction, which creates corrosion? Does this reduce risk?
That's an interesting question, and I think you have to consider lots of other things, because if you do apply a sleeve, a sleeve is a mechanical protection that goes over the pipe. It can provide extra mechanical protection, and it won't do much good against the risks of induced AC. And it will also, unless you're very careful with what kind of material you use to fill the annulus, it can also stop cathodic protection, protecting the pipe. So unless your risk assessment tells you that there's a chance of the train coming off the rails and crashing into the ground and being heavy and fast enough to crash into your pipe, and you think a sleeve will help you, my money would be on not putting it in just for corrosion protection.
Okay, thank you. Another question: how much are cathodic protection results for CIPs affected by earthing system attached, and how should an operator manage this?
Okay, well, that's a little bit off-piste because it's nothing to do with the railway interference. It's a very good question, nevertheless, and it's one I think is perhaps better to take offline because it's quite a lot more deep in the requirements of cathodic protection measurements than this presentation. But what I would say is, if you're talking about a pipe that's suffering from induced AC and you've put earthing systems on it to mitigate that AC interference, then you may need to look at a heavier reliance on electrical resistance probes and coupons rather than doing the survey. If the survey is from a railway system rather than an overhead power line, you have the opportunity to do it when the trains are not running, because they're normally timetabled, and I think you would be advised to do selected sections when the trains aren't running. That might be the best bet, but there are other ways around it, but they're rather more complex than that.
Okay, and there is another question: are those polarization devices expensive?
Yes, some are more expensive than others. The modern ones are electrical, and they work on various principles, but they probably range, depending on what you need them for and when you need them, anything from £1,000 up to £5,000. If you want one that's certified explosion proof, then they're up in the £5,000 or more. I'm not really up to date with the cost of these things, but I think if you weigh it against the consequences of a leak caused by AC, they're all cheap. And I should say that I did work on one project where the AC interference was so great that the pipe actually was holed before it was even commissioned. So if you do have an AC problem, the corrosion rate can be enormously fast.
Okay, and the last question: how does the depth of the pipe affect the corrosion, the effect of AC current?
Another very good question. You need to get quite deep before you have any problems, before the problems are eliminated. This is because of the cancellation effect of the electromagnetic and the electric fields. So unless you're going deeper than about 1 kilometer, you are still going to be affected by the magnetic field. But the magnetic field itself does drop off, does attenuate as an inverse square law. So it's the inverse of the square of the distance. So you'd still have to get very deep before it didn't have an effect.
Okay. Okay, thank you very much. Very interesting session, Ken. So thank you very much again.
You're very welcome, and thank you for the interesting questions.
And then, yes, thank you all for listening. And then please do look at Pipeline Industries Guild events site for future events. Please drop us comments if you've got any more questions. Please drop me a line or to events, Pipeline Industry Guild events. And then, yeah, thank you very much for listening and joining, and we hope to see you soon.